Welcome back to Valiant PE. Today's topic, Hooke's Law, strain, and elongation. Let's go. All right, we're going all digital today. We're going to go straight into a problem. I'm going to solve it, and we're going to come back through and talk about what makes it a PE level problem. So before we do any question solving on an exam, every time we go to a new question, we're going to do our pre-question ritual. Do whatever makes you feel comfortable. Find something that you like. I like to take a deep breath and then read the problem slowly and then immediately write what I'm solving for as soon as I'm done reading. So here we go. A steel rod is cut and machined to the dimensions shown. Assume the modulus of elasticity for the steel is 30 million psi. Find the load required to cause the steel rod to just reach its elastic limit of 36,000 psi. So we've got some imagery on the right. We've got our answer choices. First thing I'm going to do is write what I'm solving for, which is force, the units, pounds force. All right, let's go straight into it. First up, going to be Hooke's law. Stress is equal to Young's modulus times strain. In this case, my Young's modulus is 30 million psi, and my yield stress is 36,000 psi. I'm going to rewrite that in form of strain, yield stress over Young's modulus, and we're going to solve for that, put some numbers to it. 36,000 psi over 30 million psi. PSI's cancel, and my strain value is 0.0012. That's dimensionless. Now I'm going to write another strain equation, delta L over original length, and rewrite it in terms of change in length. Then I'm going to quickly just convert my original length from feet to inches. 12 inches, 1 foot. Feet cancel, gives me 132 inches. And I'll solve for change in length. Oops, excuse me. Strain times original length. Let's plug in some values. 0.0012, that's my strain, which is dimensionless times 132 inches. That gives me with a change in length of 0.158 inches. Okay, now critical to this problem, I think, is the fact that change in length is equal to elongation. So I'm going to write my elongation formula, which we've seen a bunch of times, PL over AE, and I'm going to rewrite it in terms of P sub y, which is my force at the yield point. Now in this formula, L is equal to original length, and my area, which I can quickly solve for, pi over 4 d squared equals to pi over 4, 0.798 inches squared, and that came straight from the imagery, and that gives me 0.5 inches squared. So now let's plug in, let's solve for P sub y. Got my elongation in inches, my area in inches squared, and my Young's modulus, 30 million. Going to write out PSI there. Over 132 inches, my original length. Now let's check our units. Inches cancel, inches cancel, inches squared. Left with pounds force, that's great. 17,955 pounds force. Call that our answer. Now, let's scan up to see if we have an answer that is close to that. And you can see that we do. Answer B. So I think that's a pretty good guess. We've got, remember our value here was 17,955 pounds force. That's really close to 18,000. We're going to go with 18. Now, let's talk about what makes this problem a PE level question. First up, we've seen this a bunch of times. It's multi-step. Even if it's a simple problem, it's going to be multi-step. We're never going to get anything that's just one and done. Second, we've got multiple concepts all jammed into the same question. Now this was like a 5 or a 6 step question, and we've got 4 concepts in it. First up, Hooke's law. You needed to know that well, that's a terrible sigma, goodness. You need to know that sigma is equal to Young's modulus times your strain value. You needed to understand and know your strain formulas. In this case, we're using change in length over original length, and you needed to know that it was dimensionless. Second, you needed to understand your elongation formula, axial elongation, which is, excuse me, there we go, PL over AE. And you needed to know that elongation was the same thing as change in length. You needed to understand your elastic limit or your elastic point. So you need to understand that on a typical stress strain curve for steel, this is your elastic point. This is your yield stress, and the slope of this line is your Young's modulus. Now let's go back and take a look at the problem to see where these formulas came in. Okay, first up, we've got Hooke's law. That's right here. And that was the first guy that we did, this formula right here. You needed to also see elastic point. You needed to understand that sigma sub y is your yield strength, and from reading the question, that it's asking for your, what is your elastic limit? That translates to what's your yield point. All right, next we've got strain. We've got strain twice. We've got it here, and we've got it here. You see we've got one formula here, and just a rewritten formula here, another way of writing Hooke's law. So there's strain, that's in there twice. And then last we've got elongation, that's right here. That's this guy. Now, critical to this problem also is you needed to understand that change in length is equal to elongation. We'll come back to that in just a moment. So now, there's a couple more things we need to know. There's no way to solve this problem quickly if you are not familiar with the formulas involved. Let's take an example. In our axial elongation formula, PL over AE, you had to know that L is equal to original length. If you didn't know that, it's not shown in the reference manual. Second, we just talked about this, but change in length is equal to elongation. This allows you to equate your strain formula to your elongation formula. That's a terrible arrow. I'm going to rewrite that one. Oof. Okay, that's better. Now, let's look at these 4 points again here. So Hooke's law, strain, elongation, and elastic point. Of those 4 concepts, the only one that's clearly given in the reference manual is this formula. That one's easy. The rest of these, they're all hidden. So this guy is not listed. This guy you have to derive to find it. And I could not find anything in the manual that really looked exactly like this. So you had to have studied it on your own somewhere else. And the last thing that makes this a PE problem, something that we haven't seen before, but I think you'll see on the exam, nominal answer choices. We briefly touched on it, but let's look back at our answer choices again. Okay, we solved for a value of 17,955. Pretty good guess that 18,000 is the way to go. However, look at the values immediately above and below it. They're multiples of 2 of our answer. So Just because we got something that says 18, hey, we like that, that's close, that doesn't mean that we can immediately, therefore, eliminate all the other answer choices. 9,000 and 36,000 you could have gotten if you forgot to, say, divide by 2 somewhere, or use a radius instead of a dimension. I think this kind of setup is used in multiple choice problems to keep you from to make it not so easy. If you rush and you didn't divide by 2 or something, you're going to miss this problem. There's no sense missing a problem because you sprinted through it and you forgot to use a radius instead of a dimension, something like that. There you have it, guys. That's all there is for today. Remember, you don't have to be a genius to pass this exam. See you next time.